Welcome to our first video lecture for Quantum Mechanics 2. We're going to be starting a unit now on time-dependent problems. Time-dependent problems turn out to be some of the most complicated and difficult problems in quantum mechanics. In fact, I think it's fair to say that much of the research that's done in quantum mechanics is done on time-dependent problems. So what does a time-dependent problem mean? Well, it simply means that we have a wave function at time t, 0, and we would like to understand what is that wave function at time t. So we start with the Schrodinger equation. The Schrodinger equation is IH bar d by dt of the wave function psi of t is equal to the h operator acting on psi of t. So the question that's the fundamental question we want to answer is, if I start off with the state in psi of t 0 at time t 0, what state are we going to be in at time t? Okay, I'm going to go through how this works in the case where the Hamiltonian is independent of time. This is a problem that you have probably seen already in your earlier quantum mechanics class. And the strategy is pretty straightforward. Look, we're working with the Hamiltonian, so it's probably best to put things in a basis that corresponds to the eigenfunctions of the Hamiltonian. So we're going to introduce those eigenfunctions. We're going to call them ket n, and they satisfy h acting on n is equal to en acting on n. You can see that's an eigenvalue-eigenvector relationship. The en are the energy eigenvalues, and we know from fundamental theorems of quantum mechanics that the eigenfunctions of the Hamiltonian form a complete orthonormal set. In particular, they satisfy orthonormality, which means that the overlap of the state n with the state m is given by the Kronecker delta Nm. Okay, so our psi of t0 is some generic state, so we need to expand this in as a linear combination, or if you like, a superposition of the energy eigenstates. So we have a set of coefficients Cn of t0 that are multiplying each of the states n, and we're adding them up over all possible eigenstates. When we take that expression and a slight generalization of it to change the coefficients to Cn of t to represent psi of t, and we substitute that into the time-dependent Schrodinger equation, we find we get a sum over n IH bar d by dt Cn of t acting on the state n. Recall, the state n is an eigenstate. It's a stationary state. It does not depend on time, so it has no time derivative. And that's going to equal the sum over n of en Cn of t acting on multiplying the state n. Where'd the en come from? Well, the h acting on the state n, it goes right through the number Cn of t, gives me en. And so I get that nice simplification where I can replace the h by en. And now to get an equation that we can work with, we're going to multiply on the left with the bra m. So using the orthonormality, the bra m touches the bra n. It gives me a delta mn. That means only one term is left on the sum on the left-hand side. That term is IH bar d by dt Cm of t. And that is, of course, equal to the one term that is left on the right-hand side, which is Em Cm of t. Now you can see this is a first-order differential equation, but now instead of being a differential equation that involves operators, which is what the Schrodinger equation was, which is why it's not so simple to solve that equation, we now have an equation that just has numbers in it. You should know how to solve any first-order differential equation. This is a particularly easy one because it's a linear first-order differential equation. If you don't know, recall that you can divide both sides of the equation by Cm of t, then the left-hand side becomes the logarithmic derivative of Cm of t, and that's just equal to Em, and I can divide by IH bar on both sides, so it's Em over IH bar. I integrate both sides with respect to t. The left-hand side becomes the logarithm of Cm of t, and the right-hand side becomes Em over IH bar times t plus a constant. Now, if I exponentiate both sides, what you see you're going to get is Cm of t is equal to Cm of t0 e to the minus I Em of t minus t0 over h bar. Why did I write it that way? You see, we've figured out what the constants are. You see, if we take t and set it equal to t0, the exponential factor is going to become 1, and I'm just left with Cm of t0. But of course, that is exactly what the constant has to be at time t0, because that was our initial condition. So this is the exact solution to that differential equation. We can substitute that back into the definition of psi of t, and we'll get psi of t is a sum over m. That should be a sum over n, not a sum over m. Sum over n Cn of t0 e to the minus I En of t minus t0 over h bar acting on the ket n. Now that's a very important equation. It deserves a box, so we're going to put a box around it. And I would like you to take a moment now to pause this video and go through this derivation yourself. You have to recall now, since you're watching this video, it's very easy to become complacent and simply assume, oh yeah, I got it, I understand it. But that you were not taking notes like you were when I was giving lectures on the blackboard. And the only really effective way for you to learn this material is to make sure that you really can master it on your own. So I strongly encourage you to pause the video at this time, pull out a sheet of paper, and try to go through this derivation by yourself. If you need to take a look at the steps again, go backward a little bit in the video and take a look at it. And make sure that you can go through this derivation yourself. It's a very important derivation, and it helps you understand the intricacies of how time evolution works. Okay, thank you so much for doing the pause. Now we're going to move forward. There's another way that we can think about this expression that we have. We can write it as e to the minus I h of multiplied by t minus t0 over h bar. The h bar is a little hard to see, acting on psi of t0. I'm going to back up the page just a little bit so you can see the box. How in the world could that expression come out? Well, if you look below the line that I just read out, e to the minus I h hat t minus t0 acting divided by h bar acting on n is equal to e to the minus I En t minus t0 over h bar acting on n. So go take a look at that summation. I've got that expression, e to the minus I En t minus t0 over h bar acting on the ket n. I can replace that by the operator expression, e to the minus I h hat multiplied by t minus t0 over h bar acting on n. That expression does not depend on n. The operator is independent of n, so I can pull it out of the summation. What's left in the summation then is sum over n Cn of t0 n. Well, that's just psi of t0. So indeed, we can rewrite this expression as e to the minus I h hat t minus t0 over h bar multiplied by the ket psi of t0. All right, that was pretty good. We're now going to move into time-dependent problems. H of t is time-dependent if the time derivative of h with respect to time is not equal to 0. That's a time derivative of an operator, but we can take time derivatives of operator just like we can take time derivatives of functions. They're defined in exactly the same way. We take the operator at time t plus delta t, subtract the operator at time t, divide by delta t, and take the limit as delta t goes to 0. What I would like you to do at this stage is actually pause this video and think about what is a strategy you could use to try to solve the Schrodinger equation in the case where the Hamiltonian does not depend on time. This is a highly non-trivial problem. I'm not asking you to solve it yourself. I'm just asking you to think about what are options that you might consider as possible pathways by which you might be able to solve the problem. So let's pause the video now. Take 2 minutes, no more than 2 minutes, to think about this. Do a little brainstorming session. Think about what different options are. Think about what you might be able to do. And then after that, I think it's very useful for you to write down what those options are. And after you're finished with that, come on back to the video and we'll show you 2 different techniques that we can use to give it a try. Okay, thank you for coming back. I'm going to now raise the paper. We're going to take a look at one technique. This first technique simply says introduce a complete set of states n, but they're time-independent stationary states. So these are functions that do not depend on time. They do not have to be the eigenfunctions of the Hamiltonian. They do not have to be the eigenfunctions of the Hamiltonian at a specific time. They can be eigenfunctions of anything, any operator. They simply need to be a complete set of states that are orthonormal. So we can express a psi of t in terms of them with time-dependent coefficients that we'll call Cn of t. We take that expression for psi of t, substitute it into the time-dependent Schrodinger equation. Let me remind you what that is. It's right here. I h bar d by dt psi of t is equal to h of t psi of t when h depends on time. We're going to substitute into that equation. We'll get I h bar d by dt psi of t, that's the left-hand side, is equal to the sum over n I h bar d by dt cn of t times the ket n. The derivative only acts on cn of t because the states n are independent of time. That's going to equal h of t multiplied by the ket psi of t. Now if we plug in the expansion for the ket psi of t, we can re-express that as the sum over n cn of t, h of t acting on the state n. Now at this stage I cannot replace that by an eigenvalue. These states were not eigenfunctions of h of t, and even if they were eigenfunctions at a particular time, that would not correspond to something that would be an eigenfunction of h at any different time. So there's no way, no matter what static state I put in there, I cannot evaluate h of t unless there's something very special about h of t that would allow me to do that. However, I can still multiply by the bra m on the left and use orthonormality, and we'll find the left-hand side simplifies just like it did before. I get I h bar d by dt cm of t. The right-hand side does not. I'm left with the sum over n cn of t m h hat of t acting on ket n. Now that's a matrix element. So we're going to call that matrix h sub mn of t. Then we get this differential equation, I h bar d by dt cm of t is equal to sum over n hmn of t cn of t. This is a matrix differential equation. It has two things that are rather complicated about it. The first thing, we need matrix elements hmn of t to solve it. It's not that easy to necessarily calculate those. Remember, our states n of t, our states n were just some complete set of states, and h is not diagonal on that basis, so it might be complicated to calculate those matrix elements. The other thing that we have to worry about is once we've got them, this is a matrix differential equation where the matrix is changing as a function of time. Most of your differential equation classes will not tell you how to solve that. If you've took an advanced differential equations course, it might have told you how to solve the problem when hmn was not dependent on time, and in that case you would just diagonalize the matrix and then you get a bunch of decoupled first order linear differential equations. You can solve them all and then you add up all the solutions. When the function is a matrix that depends on time, and in particular if that matrix does not commute with itself at two different times, this is a very hard problem to solve. It's not one that's easy to solve at all, and in particular we really only approach problems to solve this way if they are small finite sized problems that we can fit on the computer, say maybe matrices that are up to on the order of a few thousand by a few thousand. I mean, if you really want to push this, you can probably go to a few million by few million, but it would require some special properties to be able to get that far. All right, so this first method that we tried, it was a good idea to give it a go, but it has this issue that we're still left with a rather complicated differential equation to solve. All right, let's try another way. The other way we can try is to introduce instantaneous eigenstates. Maybe this is something that you thought of when I asked you to do that 2-minute brainstorming session. H of t acting on the state n of t is equal to en of t times the state n of t. Now notice, everything depends on time. We already know that the Hamiltonian depends on time, so the Hamiltonian at one time is not the same as the Hamiltonian at a second time. So if I find the eigenstates of the Hamiltonian at time 1, those eigenstates are probably not the same eigenstates if I find the eigenstates of the Hamiltonian at time 2. So the eigenstates themselves must depend on time, and indeed, by exactly the same reasoning, the energy eigenvalues must depend on time. So we get this generalized Schrodinger equation, which says h of t acting on the state n of t is equal to en of t times the state n of t. And you really need to think about this as I froze the time t, I figured out what the operator h of t is, I diagonalized it, and I'm calling those eigenvalues en of t, and I'm calling the eigenfunctions n of t. Okay. Nevertheless, you can very easily convince yourself that these states form an orthonormal basis, as long as I evaluate both states at the same time. So The overlap of m of t with n of t is Kronecker delta mn, and the sum over m of m of t ket m of t bra is equal to the unit matrix, just like it is when we're solving time-independent problems. What we do not know is what is the overlap of eigenstate m of t with another eigenstate n of t prime. If t does not equal t prime, we have no information. We have no idea what that overlap is. It does not need to be a Kronecker delta function. Okay. At every instant t, we imagine doing a superposition to determine what psi of t is at that instant in terms of these instantaneous eigenstates. So we write psi of t as the sum over n, Cn of t, that's just a number, times the state n of t. That was the instantaneous eigenstate. That's the eigenstate of the Hamiltonian at this particular time. All right, we have our expression for psi of t. Let's substitute into the Schrodinger equation. We're now going to get two terms because there are two time-dependent terms on the left-hand side, Cn of t and n of t. So our first term involves a derivative of Cn of t. The second involves a derivative of n of t. On the right-hand side, I have h acting on this state, but here I get a simplification. Remember, h of t, it'll just go through the number, and when it acts on the ket n of t, it is defined to give us en of t. So hopefully this nice simplification is going to give us a result that is easier to work with than the one that we were working with before. To check this out, we're going to multiply by the bra m of t on the left-hand side. And when we do that, indeed the first term is going to isolate just like it always does. I'm going to get IH bar d by dt of Cm of t. The second term, however, does not. I'm going to have IH bar sum over n Cn of t, m of t, d by dt, n of t. Now you might have thought, well, that's evaluated at the same time. Can't I figure out what that is? Remember how a derivative is constructed. To construct a derivative, I need to know the wave function at a time t plus delta t, subtract the wave function at time t and divide by delta t, and then take the limit as delta t goes to 0. So the derivative really does depend on two times in some sense, and because we do not know what the overlap is between two matrix elements at two different times, we simply do not know what the matrix element of this derivative is. On the other hand, the right-hand side does simplify just like it did before. When I multiply by that state m of t, the orthonormality gives me a Kronecker delta function. I get Cm of t, Em of t. In general, it is not easy to work with this middle term, the matrix element of the derivative. But we can get some identities. So let's take a look at how far we can push this. So note that the overlap of m of t with n of t is equal to delta mn. The right-hand side is independent of time. So now if I take a derivative with respect to time, on the left-hand side I get two terms. One is a derivative with respect to time of the state m of t overlapped with the state n of t, plus m of t overlapped with the derivative with respect to time of n of t. Now that's not exactly giving us the one term we wanted, which is the second term in that expression, but we know the sum of those two expressions is equal to 0 because delta mn doesn't depend on t, so its derivative is 0. Now let's take this a little bit further. Let's look at what happens to the instantaneous eigenvalue equation when we differentiate it. Let's start from h of t, n of t equals en of t, n of t. We take the derivative. We're going to get two terms on each side. First, we're going to get a derivative of h of t. Then we're going to get h of t acting on a derivative of the state. And that's equal to a derivative of en of t times n of t plus en of t times a derivative with respect to time of n of t. Let's multiply again by m of t. As you can see, there really aren't that many things we can do. And one of the tenets that we like to follow is use what you know and use only what you know. So one of the few things we know is this orthonormality relation. So let's multiply by m of t and see what we get. The first term is just a matrix element. There's nothing I can do with it. M of t, d by dt, h of t multiplied by n of t on the right. The second term is also complicated, but notice I can pull out the operator because h of t acting on m of t will give me em of t. So I will get em of t times the overlap of m of t with this derivative d by dt of n of t. On the right-hand side, the first term is simple. That is going to give me a delta function overlap, so I'll get d by dt en of t times delta mn. And then the second term is again the same complicated expression that I'm trying to work on. I'm going to get an en of t times m of t overlap with d by dt of n of t. Okay, now the delta mn is a little bit complicated. It's easier for us to think about this as two separate cases. Let's first consider the case where m equals n. When m equals n, these two offending terms that involve m of t d by dt, now m of t instead of n of t, because I picked n equal to m, I have exactly the same term on both sides because there's an em of t on the left-hand side, and the en of t becomes an em of t because n equals m on the right-hand side. So both those terms are the same. I can cross them off. They're gone from the expression. The delta mn becomes 1, so I'm left with a simple expression that the overlap of n of t, d by dt, h of t, n of t is equal to the time derivative of en of t. Those of you who have seen something called the Fineman-Hellman theorem will immediately recognize that this is exactly the Fineman-Hellman theorem. If you've never seen the Fineman-Hellman theorem and you always want to know what it is, there it is sitting right in front of you. Okay, that's a nice expression when m equals n. Let's now take a look at the case where m does not equal n. In that case, the Kronecker delta function disappears. I still have the complicated matrix element, but you see the other remaining matrix element is this m of t derivative with respect to t of n of t, and it has two different coefficients. One is em of t, the other is en of t. Let me bring both terms to the right-hand side. Let me gather them together, and then divide by the difference en of t minus em of t, and we get this very nice expression that m of t d by dt n of t, that's the right-hand side, is equal to this left-hand side, m of t d by dt h of t n of t over en of t minus em of t. Now we're assuming here that our system has no degeneracies in it, because if it had degeneracies I couldn't do this division. So let's assume that for the moment that our system had no degeneracies and it was okay to do this division here. And you see, you might not recognize it, but this is a remarkably nice result. We have gone from something that would be very difficult to calculate, the time derivative of a matrix element that I calculate by looking at the eigenfunctions from diagonalizing two different Hamiltonians. That's an unpleasant, complicated problem, to evaluating a matrix element between just eigenfunctions with a time derivative of the Hamiltonian. That time derivative I can calculate much more easily than the time derivative of the wave function. So we use that and plug into the equation that we derived above, and we get this beautifully nice equation, IH bar dm dc m of t by dt plus IH bar cm of t m of t d by dt m of t. Unfortunately, that's the one term that's left over because we can't replace the term when m equals n because we got no expression for what that derivative was. Plus IH bar sum n does not equal m, cn of t, m of t d by dt, h of t, n of t over the ratio over the difference en of t minus em of t, and that will all equal cm of t times em of t. Now we got pretty far. We got it into terms that we could evaluate nearly everything. We're still left with this one offending term, m of t d by dt m of t. And while that is something that you could in principle calculate, it's not that easy to work with and it's a little bit hard to deal with. And so this technique has not fully given us a solution to the problem that we would have liked to have been able to achieve. Okay, we're about halfway through the lecture. This is a good time for us to pause. You might be surprised that this lecture is going much faster than we do it in person. Remember, I'm not writing things out on the blackboard, but remember again, you are not writing them in your notebooks either, and so it's very easy to forget what we have done. So again, this is a very good time to pause, go take a short break. I also encourage you to get out a piece of paper and work through this derivation that we have just worked through. And we're going to come back and get on with the second half of the lecture.